Hello, Georgi Romanic here. Today we are going to explore the beauties of the Charles law. This is another experimental law highly related to kinetic theory of gases and equation of state. Similar to Boyle's law or Boyle-Mariotte's law and Gay-Lussac's law that I described in previous videos, Charles law was also discovered before the entire kinetic theory of gases was set up as a theory. Charles law says, for a constant pressure and number of atoms in a volume, volume and temperature are directly proportional. That means when we increase temperature, volume increases. Well, that makes sense. When we heat up a volume of a gas, well, the volume tends to increase. That's Charles' law. Let us now see how Charles' law relates to the equation of state of an ideal gas. Charles' law says that volume divided by temperature is constant if pressure is constant. We can easily derive this law from the equation of state for an ideal gas, where pressure times volume is n r star T, where T is absolute temperature, r star is universal gas constant, n is number of moles of the gas in volume V, and P is pressure. So you see, if pressure is constant, I can move it and combine with n and r star, which are both constants, so we get simply that V over T is therefore constant. If you want, it's very simple to represent this law graphically. If we have temperature here and volume over here, you will see that their relationship is linear, like so. The relationship between volumes and temperatures is such that volume in gas 1 divided by temperature in gas 1 is volume in gas 2, temperature in gas 2. In atmospheric sciences, we do not use this law as often as, for example, Dalton's law that I described, or Boyle's law, and so on. But nevertheless, it is important law and it is good to know it. Let us try to do an experiment related to Charles' law. Here I have a balloon and here I have a source of heat. This quick video was on Charles' law. The next video will be on Avogadro's law, and that's the last of the experimental laws related to equation of state of an ideal gas and kinetic theory of gases. Until then, goodbye.